Hello everyone, I am Ziao Gang, an artificial intelligence instructor from the Talent Ecosystem Development Department. In the previous section, I explained activation functions to you. In this section, we will focus on regularization. Regularization is a very important and effective method in machine learning to simplify generalization error. In machine learning, we also have L01, L2 norms as parameter penalty terms. In deep learning, what are some methods we can use to prevent overfitting? In other words, what regularization methods do we have in deep learning? Let's take a look. Similar to machine learning, we have L01, L2 norms, and then there is training set augmentation, such as adding noise, and data transformation to increase our sample size. Then we have the unique method dropout in deep learning. Dropout is a method commonly used in our neural networks to prevent overfitting. Finally, I will explain another method, a simpler one, called early stopping. Let's take a closer look at what our L01, L2 norm looks like. If you are familiar with machine learning, I will lead you through a review here. For students who are not familiar with machine learning, let's learn about parameter penalty together. Parameter penalty. That is, adding a penalty term to our objective function, which is both our objective function and our loss function, called parameter penalty. One of its alphas is a penalty factor for us. This part of ours is a penalty term for our parameters. It's an omega penalty term. Our omega theta is our penalty term. Why does this area make our learning efficiency lower? Or can it prevent overfitting problems? Let me explain this to everyone. Because our objective function aims to make this error gradually approach zero, it proves that our predicted value is equal to our actual value. Since we want to constrain it to be equal to zero, we need to constrain this new objective function to be equal to zero, close to zero, so both of these are approximately equal to zero. If our penalty factor is particularly large, then our parameters will be particularly small. In this way, it will constrain our parameters, causing them to update to a minimum value to prevent the occurrence of overfitting. So let's take a look at it. The larger the alpha, the more severe it penalizes this parameter. Usually, for the parameter theta, we only apply constraints to the weight, not to the bias. Why? The main reason is that this bias term generally requires less data to fit accurately. If you punish it again, it will lead to an underfitting phenomenon. So our main focus is generally on our weights. Okay, let's take another look at one method of our parameter regularization called L01 regularization. L01 regularization mainly makes our omega theta equal to a form of absolute value. This form, that is to say, it can gradually decrease our weight values, step by step. Some weight values have a very small value, which is equal to zero. In this case, we can also indirectly understand it as being able to perform feature selection. Another regularization method is to transform our regularization term into a function, in a quadratic form. In this quadratic form, it allows our parameters to gradually approach a small value, close to zero. But it cannot make our parameters equal to zero. So the difference between our L01, L2 regularization is that the L01 regularization term can generate a sparser model. In other words, when using L01 regularization, we can directly shrink the parameters to zero, which also serves as a feature selection. This is what we just mentioned, why they can do feature selection. Let's first look at the difference between the two from a probability perspective. First of all, many parameters are approximated, which is equivalent to adding a prior distribution to the parameters. The parameters of L2 are equivalent to parameters following a Gaussian distribution, while L01 is equivalent to following a Laplace distribution. So this is one of its main differences, which is also an important distinction between these 2 points. Everyone can understand these 2 points. If you are not very clear about mathematics and not very familiar with it, you can also start by learning and consolidating high-speed Laplace distribution, Gaussian distribution, and then come to understand this area of knowledge. Along the way, we gain a clearer and more intuitive understanding of the specific distribution of these two. In other words, L01 regularization can assign some parameters to zero, leading to the deletion of some information, thus achieving the function of feature selection. Now, let's take a look at another regularization method we have, which is dataset augmentation. Data augmentation is also commonly used in our machine learning. If its sample size is not large enough, you can increase our samples to prevent overfitting. However, deep learning requires a large number of samples, a big data, a form. Therefore, in different fields, the methods for handling dataset expansion are not the same. Let's take a look at how computer vision expands datasets for images. rotate and scale our For example, in our handwriting recognition, if the original sample is 6, we can rotate it to become 9, or shrink it to become a small 6. Then this new sample generated by these two is added to our original sample. In speech recognition, we can introduce random noise in the field of speech recognition to address different noise scenarios. In the field of natural language processing, that is, dealing with text and speech, we can perform synonym replacement. In other words, for example, with this word replacement, we can change it to correction, as well as other words with the same meaning. Noise injection can be applied to the input layer, hidden layers, or output layer. For example, in our softmax classification problem, we can use label smoothing technique to add noise. For example, adding noise to our positive and negative samples, 0, 1, the corresponding probabilities become k divided by 1 epsilon, and 1 minus k divided by 1 minus k1 epsilon. This form increases our noise. We can see that data augmentation is actually a time-saving and effective method to avoid overfitting, without requiring a lot of effort, just by increasing your dataset. Let's take a look at another method, which is also commonly used in neural networks, and is unique to neural networks. Dropout is currently a widely used, simple regularization method that was proposed in 2014 and has since been widely adopted. Simply put, what is a training of drop? It means to drop first, and then out. That is, when dropping, you must randomly discard a part, randomly discard what you discard later, and then what is the final network structure of your network, based on this network, and then update the parameter. After updating one parameter at this point, you proceed to randomly discard a portion, and finally obtain a result, a network, followed by updating parameters based on this network. This way can help our parameters achieve the best result, and then avoid the overfitting issue. So on the right side, this diagram has actually completed the dropout process. UX1 takes the input from the previous time step, and the current time steps, X1, X2, along with the previous time steps UX2, continuously producing output until Y is obtained. With this network, we proceed to update the parameters. After the update, when updating the parameters in the next step, we still randomly prune the network, apply dropout, and continuously update our parameters. This is a core idea of our drop. In addressing the overfitting issue in neural networks, dropout is more effective than our parameter penalties and sparsity constraints. In other words, it is a more effective method to prevent overfitting. At the same time, it also has a relatively low computational complexity, with very low computational complexity. Another point is that when we have a small training sample size, it has a negative impact. When our data volume is small, the performance is not good. In the dropout training process, randomness is not sufficient nor necessary, and this point must be remembered by everyone. Another good point is that it can construct invariant shielding parameters, such invariant shielding parameter. By using these shielding parameters, it can obtain an optimal solution, leading to our function obtaining the best solution. Here are some advantages and disadvantages of the dropout method. After discussing this dropout, let's take a look at the last method, which is also a relatively simple method, that is to stop one of our trainings, early stopping. For example, if you have iterated 100 times and encounter overfitting, you can reduce the number of iterations to 50 or 60, then stop the training of your model early, so that the parameters stop training when they reach the best solution. In this way, there is no need to excessively study some information in our training set again. This is one of the methods we are going to explain and introduce to everyone to prevent overfitting. We hope everyone will consolidate each method. In the next section, I will focus on explaining the optimizer to everyone. What is the specific main function of the optimizer? Why did the optimizer update again in the gradient descent algorithm? And what are the current optimizers being used, their respective advantages? Okay, in the next section, we will give everyone a detailed explanation. In this section, thank you all for watching and learning. See you in the next section. Goodbye.